So this is joint work with Ayesha, Bajwa, Nancy Lynch, and Frederik Mallmann-Trenn back when we were all at MIT. So what we looked at was developmental patterning. So the question is, how do tissues form in a scale-invariant way as organisms develop? Because you'll notice that as organisms grow, they are still roughly proportional. And we want to model that, or we want to look at that from a theoretical computer science perspective. So way back in 1969, this was defined as the French flag problem. And the idea is, we have a set of cells, and they need to determine their type from positional information. Positional information was thought to come from graded chemical signals, and these are known as morphogen gradients. And this was later verified experimentally. So to give an example, here we have neural tube patterning, and this is actually the cells differentiate based on concentrations of 3 different morphogen chemicals that form a gradient. These are SHH, BMP, and WNT, and that is enough for these cells in these neural tubes to differentiate in this pattern, no matter what size the neural tube is. Similarly, for flies, there are 2 morphogens that determine the patterning of a fly embryo that corresponds to adult flies as well. So, first we want to simplify the problem a little bit even further. So we looked at the 1D case, the French ribbon problem. So here we're gonna represent cells as computational agents that are initially uncolored, and they have to choose a color from 3 or k colors. For 3 would be the French flag, and for k it might be some other pattern. So after running some algorithm, they need to choose colors such that each band is equal in size to every other band within a single cell of tolerance. You can imagine that this can be extended to other patterns than simply 3 bands of the same size, but this was sort of a simple example that seems to capture the problem pretty well, and it has been studied before in other contexts. The French flag is simply the 2D version of this, and in the paper we also discuss approximate flags. These are flags with bands that are not exactly equal in size, and you can check out the paper for those, but I won't be discussing those much in this talk. So our first model, first computational model, is simply we provide positional information to agents directly via morphogen concentrations. So you can imagine morphogens are released by designated source agents in the line or in the grid, in the flag grid, and we assume enough time has passed such that the concentrations are not changing over time, and that the agents know the gradient function of these concentrations. Here you can see an example of this. We have a set of cells on the left here, and on the far left side are the source agents. They release some morphogen chemical that forms a gradient along the rest of this set of cells, and it's roughly a inverse power law. So the algorithm is simply agents receive concentrations from sources at each endpoint of the line, and using these concentrations, and knowing that the gradient function in this case is an inverse power law, each agent can choose a color such that the ratio of these measured concentrations is at most this expression here is z minus 1 over k minus z raised to the a power, where a is the exponent of this inverse power law. So this is pretty simple. All agents have to do is do some simple arithmetic, subtraction, division, and repeated multiplication. And that is enough to determine whether an agent's in the first third, middle third, or last third of the line, assuming that there is a source agent at the start and at the end of the line. So this is a pretty simple case, and we were wondering, is the 2D case just as easy, or is there, or are there problems that arise? And it turns out that we have 4 source agents, one at each corner, where the 2 on the left and the 2 on the right release the same morphism. It is impossible to even approximate a French flag. And that's because what we can do is we can construct a new flag, given a flag, such that 2 agents of different colors, one in each flag, measure identical concentrations. So this is an indistinguishability argument. So clearly we need more than 4 source agents, or more than 2 different morphisms. But we played around with this and we couldn't find a way to do it. So we decided that for now, perhaps this model is not, it was not going to be very fruitful. So we decided to go to check out a different model of what's happening in the French flag problem. So here we move to message passing. So basically it's a congest model. Each agent is connected to its neighbors. In a line, it's left and right neighbor, and in the French flag, it's left, right, up, and down. And each agent may send each neighbor a small message every round. And time occurs in synchronous rounds. Agents also know additional information that they know directions of their neighbors, and we made the problem a little bit harder for ourselves by saying that all agents are initially asleep. And by asleep, we mean they cannot send or receive messages. They cannot send messages or perform computation. And the reason for this is we imagine it's more plausible that not all the cells in an organism are going to know, are going to have a sense of time and start at the same time. What's more likely is some process will start at a single point in the organism, and the algorithm will have to continue from there. So we have some starting agent. It can be chosen arbitrarily, and agents wake up after receiving a message. So unlike morphism gradients, this is more comparable to cell-to-cell communication. And this is, for example, in neurons, there are synapses that communicate. Neurons communicate over synapses with chemical or electrical signals So it's no longer sort of global position, but rather local communication. So I'm just going to look at real quick our results. We came up with 4 different algorithms for this problem, mainly because we couldn't find an algorithm that was optimal in all senses of the word. We found that we found one algorithm that was optimal for the number of rounds, one for the memory per agent, and one for bits per message. I'm going to go over 3 of these very briefly, but the main sort of question is, can we somehow find algorithms that achieve all these optimal values in a single algorithm? So our exact count algorithm is probably our simplest. Each agent is going to maintain a count of the number of agents on its left and on its right, all the way to each endpoint. And then all I have to do is take the ratio of the number of agents to the left and agents to the right, and compare it to n over 3 and 2n over 3, which are the boundaries of a ribbon of size n. And you can imagine this generalizes to k colors very easily, assuming you have these counts. So I'm going to run through these. What's nice about this is that it can be used asynchronously, unlike most of our algorithms. So what's going to happen is an agent's going to wake up, and then from then on, when an agent wakes up, it'll send its left count to its right neighbor +1. So this starting agent had zero neighbors to its left, so it'll send the number 1 to its right, and so on until we reach the end. And then the last agent will know that it has no right neighbor, and it has heard that it has 5 to its left, so it can guarantee that it should be the color red. And now we can just repeat the process in the other direction. And as we go, every agent is going to have enough information to determine its color. So we require login bits per message because we have to send a count, which is log base 2 of n in either direction. And what I've shown you will run in roughly 2n rounds, but we can actually improve this to 2 minus 1 over kn rounds. I'm not going to go into the nitty-gritty details. It's just a bit of arithmetic. But the idea is that when an agent receives its first count, it will start a timer that increments every round. And what you know is that this app now requires synchronous timing. Is that when it receives the second message, that'll be half the time on its timer will be the distance from it to the other endpoint. So if the timer reaches a very large value, then the agent knows it must be very far from its other endpoint and can safely assume that it is the color of one of the outer sections. It turns out we can't do any better than this, and I think in the interests of time, I'm going to skip this proof idea, but you'll have to take my word for it or read the paper. But our next algorithm, the silent count, is basically taking this idea of using time to determine the count a step further. So instead of sending a count from agent to agent, we're only going to send a ping, which is just a bit, and the bit is going to be passed from agent to agent in a single direction and then returned in the opposite direction. And each agent can determine its the count of agents on either side based on the time between pings. Now this makes it a lot harder to achieve 2 minus 1 over k times n rounds, but it does achieve it in 2n rounds with constant size messages. So unclear how to improve this, but we have hope that future work will find it. So we also had an approximate algorithm. That one did not produce an exactly correct French flag with high probability, but it turned out it got very close. Well, it can achieve an epsilon approximation for our definition of epsilon approximation using very few bits per message and very low memory per agent. But I won't go into that in this talk. What instead I'm going to talk about is our algorithm that is arguably closest to optimal, which is our bubble sort algorithm. And the idea here is that we want to assign colors in the required ratios without worrying about order. And then after we have the correct ratio of colors, then we sort the colors among the agents. So we have swaps happen by even or odd agents depending on the round, so that no conflicts occur. And this requires O-log k memory operation and bits per message. The main downside is the number of messages that's used in bubble sort, which is n squared, while all the other algorithms are only a linear number of messages over the course of the whole algorithm. Right. So this is pretty standard implementation of bubble sort once we have the colors, and that's so basically what we're going to do is every round, so the first round, the starting agent is going to choose a color arbitrarily, and then at every round, each agent is going to simply broadcast its color to its neighbors. And based on the first color an agent hears, or receives, it simply assigns itself the next color in some round robin order of the colorings. So if you just look at the top, it would look like, blue, white, red, all the way down the line, assuming we didn't do the swaps. But here, after the fourth round, the third and fourth agents know each other's colors, and so they know that they are out of order, so they can perform a color swap. They don't even have to communicate about this because they know what the correct state should be. And blue has to come before red, so they must do a swap. So the algorithm just continues that way, where swaps happen. Swaps don't happen next to each other, so that there are no conflicts. And at the end of once a message reaches the right endpoint, we have the correct number of red, white, and blue, but they are not in the right order. So once we reach an endpoint, we can send a message back saying, "Okay, the algorithm is over," just so that all the nodes know to stop. So we had two models and two approaches to this problem, both this concentration model and a message passing model. In the concentration model, we found that in the 1D case, it's very easy, and in the 2D case, it seems harder. We actually checked that even with a source all across either ends of the flag, it's not enough to compute even an epsilon approximation experimentally. We did not prove this. In the message passing model, we had some trade-offs between all these algorithms. We had a simple one that finished in an optimal number of rounds. We had the silent count algorithm that reduced the message size. We had an approximate algorithm that improves both space and message size, but didn't exactly compute the French flag. And we had bubble sort, which had constant space and message size, but many messages. And I'll note that the reason I only talked about the 1D case for message passing was because once you have a ribbon inside of your French flag, it is very easy to just copy the colors up and down. So it's more interesting to think about the 1D case, unlike in the concentration model where there's no communication. So having a single line correctly calculate its colors is not sufficient. So these results are definitely incomplete. So I would love to find some algorithm that achieves all the best of all worlds. So that's an open question. Another question is, in the 2D flag in the concentration model, how many sources are required? Can we produce an epsilon approximate flag? How do we find a good solution here? Another idea is, could we combine these two models and improve on our algorithms that way? This seems like it could also be biologically possible. And finally, could we extend this to other shapes in an interesting way, or even 3D flags or sort of flag-like objects? Yeah. So thanks. That's all I have for you today. Thanks for the opportunity to speak. And if you have any questions, please let me know.
Thank you, Bertie. Now I should be hearable, I hope. One quick question, if there is one. I can admit. Anybody with a question? You posed all the questions that I collected during your talk already yourself in your future work section. So this is...
Maybe ask a question, but your mic is muted, Ludwig.
Ah.
Okay. Now you can.
Good. So just a question. So it's impossible in the concentration model, kind of no matter how you put the sources, but how about you have more than one kind of morphogen? Would you have two kinds of morphogens and then do a French flag?
Yeah, we investigated a little bit. In the impossibility result we had two different kinds of morphogens, one for the left side and one for the right. I imagine perhaps it's easier. Perhaps if we have a number of morphogens, perhaps in terms of epsilon or n, we could do better. But we didn't. We mostly focused on the message passing model after we determined that 2 different kinds of morphogens at the corners was not enough.
Thank you.
Okay. Okay. Thank you very much.